So I just wanted to finish the first video and do these two examples, which have asterisks next to them, because there are certain types of functions where our definition of the derivative, limit as x approaches 8, h of f of x plus h minus f of x all over h, simply won't work. And there's different reasons for that. And on the first two examples that we did, finding the general derivative formula for f prime of x would have worked, and then we could have plugged in a 4 and found f prime of 4, and it would have worked here, and then we could plug in a 2, and we would have our f prime of 2. But for these two types of functions, if you went ahead and tried it on your own and you tried to do the f of x plus h minus f of x method, which is a traditional form of the derivative, and gives you a general rule, it wouldn't work. So the only way to do these two is to specifically know which location you're looking for the derivative at, which is 6 in this case, and then to do the alternate form of the derivative, and you'll see how this all pans out. So if I'm looking for the derivative of this function at 6, c is 6. So it's the limit as x approaches 6 of f of x, which is absolute value of x minus 6, minus f of 6. Now f of 6 would be 0, all over x minus 6. And this limit reduces to, the minus 0 doesn't do anything, so it ends up just being, what is the limit as x approaches 6 for x minus 6 in absolute value signs over x minus 6. Now, we should all recognize that as a jump function. This is the jump function that has been shifted 6 units to the right. So the jump is happening at 6. And if you approach 6 from the left, it'll be negative 1. If you approach it from the right, it'll be positive 1. And hence, we know that the limit of a jump function at the place that it jumps does not exist. So if that limit doesn't exist, well then the derivative, or the slope at 6, doesn't exist. And let's think back to the original function and make sense of why the slope at 6 would not exist. The reason for that is because this is an absolute value function paragraph, which is a V-shaped, shifted 6 units to the right. So we are essentially looking for the slope of our function at 6, which is right at that sharp corner point, and we know from having discussed in class that when functions turn sharp corners, at those corner points, the slope does not exist, and this alternate form of the derivative shows that. Okay? Similarly, this one, which is x plus 3 to the 1/3 power. The f of x plus h method here would be very ugly. We could do it, but it would be ugly. And since we already know that this is the location at which we want to find the slope, we can just jump right into it and find g prime of negative 3. So that would be the limit as x approaches negative 3 of f of x, which is x plus 3 to the 1/3 power, minus f of c. So f of, or g of negative 3, I guess in this case, would be 0 to the 1/3 power, which is just 0, all over x minus negative 3, which will become x plus 3. And so the minus 0 doesn't do anything for us again. And if we try to find this limit by direct evaluation, you plug in a negative 3, you're going to get 0 over 0. So some manipulation is required here. Now, a 1/3 power is like the cubed root. So there is a radical happening. So we could try rationalizing the numerator. You have to be a little bit more thoughtful in how you rationalize, though, because if this is being raised to the 1/3 power, we actually need to multiply it by x plus 3 to the 2/3 power, so that when you multiply those common bases, the exponents add, and 1/3 plus 2/3 gives you 3/3, which is 1, which eliminates the exponents being there or appearing there altogether. So you just have to rationalize a little bit more thoughtfully to get rid of the 1/3 power. So your numerator is going to become just x plus 3, technically to the 3/3 power, which technically is then to the first power, but we know we don't write that. So it's just x plus 3 up top, and the denominator has this x plus 3, and the x plus 3 to the 2/3, which we're not going to multiply out. And the reason we're not going to multiply out is because by keeping them separate, it just gave us a nice opportunity to cancel. So that 0 over 0 culprit just got eliminated, and now this reduces to 1 over x plus 3 to the 2/3. So I have the limit as x approaches -3. And now I can reevaluate. And when I do that, I'm going to get 1 over 0, which is different than the 0 over 0. So I did initially get 0 over 0, which is indeterminate. It was too early to tell. Now I'm actually getting a number over 0, which does not exist. So at the end of all this, kind of like the absolute value one, we find out that the slope of our function at -3 does not exist. Now, why is that? Well, this one we knew was because of a sharp corner point, because we knew a little something about what the original graph looked like. I don't know that any of you know what that original graph looks like, but I'm going to show you, and then you'll be able to make sense of it yourself, why at -3 the slope doesn't exist. So here's our image, and here's -1, 2, 3. And the curve certainly looks smooth there. It's not hitting a sharp corner point. But what happens is just for that instant, this is a little wiggle, but it's wiggling vertically. So we're used to wiggles like this, where instantaneously right there they have a slope of 0. Well, this one is wiggling like this. So instantaneously right there we have an undefined slope. So like every location has a tangent line, and the slope at that location is the same as the slope of its tangent line. So for example, right here, whatever the slope of that tangent line is the same as the slope of the function at that location. Well, right here, your tangent line is a vertical tangent line. So the slope of a vertical line is undefined, which means the slope of your curve right there at -3 is undefined. So a corner point can be the causation for derivative not existing. Sometimes if the function doesn't exist at all, that would be the reason why the derivative doesn't exist. And sometimes it's because the graph actually has a vertical tangent there, and so the slope at that location does not exist. So that just finishes up the notes for you, because we didn't get through all 4 of these, and your homework is there at the bottom.